things that we're going to talk about today, of course, with myself are the weeds aspect for the exam. We're going to cover two different areas. We're going to talk first about the weeds in particular. We're going to talk not specific species. We'll spend time talking about identification, characteristics for identification, weed biology and ecology. In the weed science area, for many, many years, we've dealt primarily with how do we control the weed. And since probably the 60s and 70s, of course, we've concentrated on chemical control methods. We really have not put that much of an emphasis on the biology and ecology of the weeds. We've known how to kill them, but we're not that familiar with the weed themselves. So we're seeing a little bit more research effort now being generated to look at the biology, the life cycles, and the ecology of several of these weed species. Then we'll also talk somewhat on herbicides themselves. How do we manage herbicides? What are some of the principles governing the effectiveness of a soil-applied herbicide? What are the factors governing the effectiveness of foliar-applied? And hopefully, if we stay on track and have enough time, we can cover some of the principles of herbicide mode of action. Now, as we say up here, as we get into weed management, weed identification, of course, is essential. It's the first correct step in weed control. Now, we're not going to have any specific slides of weed specimens, but there are several excellent references available for this. The Illinois Scouting Manual has several species in there. Other color publications are also available, so there's really not a lack of references available for you folks to look at to identify specific weeds, either by drawings or by color photographs. So let's spend a little bit of time talking a little bit about weed ecology and biology. There's a few terms that we need to define first off that generally you find used quite often when you're in the world of weed ecology and biology. And the first one is dormancy. Now, dormancy refers to a condition of viable seeds. And by viable seeds, we mean it's those seeds that are alive and one day would be able to germinate and produce a new plant. It's this condition that delays or prevents the germination of these viable seeds. Now, there are several different terms that fit under dormancy. There can be instances of innate dormancy, induced dormancy, and enforced dormancy. But generally, overall, the dormancy is a state of condition of seeds that prevents their germination. Another term that you frequently encounter is allelopathy. Now, an allelopathy is a chemical that's actually released by one particular plant species that inhibits the growth of another plant. A lot of these allelopathic substances are even exuded out through the root system, and they more or less it gives that particular plant that produces these allelopathic compounds a competitive advantage. Those compounds, if they inhibit the growth of neighboring plants, then the plant that exudes these allelopathic materials has a competitive advantage in that environment. Vegetative reproduction versus seed reproduction. Now, when we're talking vegetative reproduction, we're dealing primarily with perennial species. And we'll go through weed life cycles in a little bit, but to give you a little introduction, of course, perennials are those plants that can live more than 2 years. Generally, if conditions are favorable, many perennials can live many, many years. Now, vegetative reproduction is the multiplication or reproduction of plants by non-sexual means. By that we mean there's no seed involved. There's no union of pollen and seed or ovule. So it's a total vegetative reproduction method. Now, there are several types of vegetative or structures that can lead to vegetative reproduction. I'll give you some examples. Rhizomes or tubers or stolons are some of those vegetative, what we call propagales, that can lead to the formation of new plants without seed. Now, we contrast that to seed reproduction, which is a true case of sexual type of reproduction. Now, as we deal with seed production, as you well know in your dealings with weeds, weeds differ in the number of seeds that they can produce. A given species can produce more or less weeds than another species. And we give you the example up there of a giant foxtail plant that may, in a relatively good year, produce close to 10,000 seeds, versus something like red root pigweed, which may be upwards of over 100,000 seeds. So between species differences exist, as do environmental conditions also affect the number of seeds produced by a particular plant. Let's move now into weed identification. Now, as we said at the outset, identification is more or less the cornerstone for weed management. We have to know what we have out in the field in order to design an effective control strategy, be that either mechanically or chemically. Now, if we're talking chemically with herbicides, we have to realize that our selective herbicides that we use in our crops, in corn, soybeans, wheat, whatever, the selective herbicides generally, of course, do not control every different weed out there in the field. So we need to know what we have. For example, if we go out and scout our soybean field, if we're on a planned post-emergence basis to control broadleads, if we go out and we see that we have the predominant weed out there is black nightshade, let's say, our choice will probably not be Classic and Pinnacle for that particular field, because those two particular compounds are weak on black nightshade. But if we didn't go out and identify that particular weed as black nightshade, and we were dead set to use those two chemicals, we're probably not going to get a very good return on the herbicide investment. Now, as we classify weeds for identification, most references that you'll find will break down the classification into grasses, broadleaves, and sedges. So we'll start out first and talk about grasses. Now, true grasses have there are some characteristics of a true grass. They have round stems, hollow internodes, and two ranked leaves. Now, there are some variations in a couple of these characteristics, but overall, most true grasses have these characteristics to them. Now, several of the features that we commonly use for identification purposes include the blade, the leaf blade itself, what the margins of the leaf blade look like, are they rolled, are they flat, how wide is the leaf. We can look at the ligule. The ligule is a very useful characteristic for identification of the various grass species. Auricles, and of course the presence or absence of hairs or pubescence. So if we first look at the leaf blade, of course the leaf blade is the upper expanded portion of the leaf. Now there are several different shapes of leaves, of course, that may be flat, the margins may be rolled, the leaves may be somewhat twisted counterclockwise as they emerge from the growing point of the plant. Some of the particular weeds that we deal with, in particular, let's say fall panicum, has a very distinctive midrib on the leaf that's often used for identification purposes. So there are several things on a leaf blade that we can use for identification. But probably when I look at a particular grass species, the first thing I'll look at are the ligules. Number one, we have to determine if ligules are there or if they're absent. Now, the ligule is located on the inner side of the leaf blade, and it appears as the extension of the sheath at its intersection with the leaf. So if it's there, if you peel back a leaf, if you hold the stem in one hand and peel back the leaf, look at where the leaf blade joins into the stem. If the ligule is there, it'll appear as a small extended portion coming out of the stem. Now, in ligule characteristics, we can either have ligules. Certain species that we deal with do have ligules, primarily the foxtails. Yellow foxtail, green foxtail, and giant foxtail all have ligules, as do the panicum species. These ligules are hairy ligules in the foxtails, hairy ligules in the panicums. Another general type of ligule is membranous ligule. And good species there to look at are the crabgrasses. They have a membranous type of a ligule. And of course, as we said, as we started talking about ligules, they're either there or they're not. And probably our most common example in Illinois, at least, of a grass species that does not have a ligule at all is barnyard grass. If you peel back the leaf, look at that junction of the leaf and the stem, there will be no ligule there at all. Now, auricles are a finger-like projection of the blade that extends around at the collar of that leaf. Now, we can say in Illinois, at least primarily, most of our weedy grass species do not have auricles. Probably the one that we deal with the most in Illinois that does have has auricles would be quackgrass. And of course, that's a cooler grass that we find primarily up in the northern part of Illinois. If we go down into southern Illinois and the warmer regions, we don't generally have to contend with quackgrass. So auricles, you probably won't be using that much for identification here in Illinois, but in adjacent states up in the northern U.S., There are several other species that they have to contend with that do have auricles. Now switch over to broadleaves. How do we identify broadleaves? Well, there's several characteristics. Broadleaf, as you well know, vary in shape, in size, in color, in texture. So there's a whole wide range of characteristics that we can use for broadleaves. Several that we'll talk about here briefly include the type of the leaf, the arrangement of the leaf, and the root system on the broadleaf plant. Flower characteristics are also very useful for identification. Unfortunately, by the time that the flowers are present and we can use the flowers for identification, we generally have passed, of course, the optimum time for control. By the time, of course, the broadleaves have emerged, or the flowers have emerged on the broadleaves, of course, we're very near getting close to harvest time, and any yield loss caused by the broadleaves has already occurred. Leaf type and arrangement. This is probably one of the most useful characteristics for broadleaf weeds. And we have to define a true leaf. Now, broadleaves, most broadleaves, of course, are dicots, and by that we mean the first leaves that come out are two leaves. The cotyledon leaves are two leaves, where grasses are monocots. They only have one cotyledonary leaf. Now, all the leaves that are produced after the cotyledonary leaves are the so-called true leaves. So if you happen to read a chemical label that says for a particular species, maximum leaf stage is 4 leaf stage, those are counting only the true leaves. The arrangement of these leaves on the broadleaves plant can vary from alternate, where we have one leaf on one side of the plant at a node with an alternate arrangement. The next leaf will come out on the opposite side of the stem at the next node. Just almost a stair-step effect up the stem of the plant. Or the opposite arrangement. With an opposite arrangement, we have leaves coming out at the same location on both sides of the stem. Now, there's several leaf types or leaf shapes. And in the scouting manual, as I referred you to earlier, they actually have some picture drawings of some of these types of leaf shapes that you can run into. The root systems of broadleaf plants can also be useful for identification. We also can look at root systems for grass species. If we're dealing, let's say, with a perennial grass, we generally would be looking at some type of an extensive underground root system, whereas if we're dealing with an annual grass, it's probably just going to be a very shallow, fibrous type of root system. We can also use these characteristics for broadleaves. Of course, the roots provide anchorage for the plant, are the main areas of absorption for water and nutrients. We have different types of root systems. We have the tap roots. A good example of a species with a taproot system would be velvet leaf. A fibrous type of a root system. If you ever pull up a nightshade plant out in the field, it's got a very fibrous type of a root system. There's really not one distinct taproot that goes down. It's more like a lot of small roots that extend extensively through the soil. And also a rhizome root system. Now, if you remember back when we briefly touched on perennials, we talked about a rhizome system as one of these vegetative propagales that can spread this particular weed without seed. The extensive root systems, and this is why we have trouble controlling perennials, either with tillage or chemically, because as these very extensive root systems that we typically find on a perennial species, in order to control that plant adequately, either mechanically or chemically, we need not only control the top or what's above ground, but we also have to control that extensive root system. And that's why perennials are generally much more difficult to control than annuals. Let's switch now out of the identification and talking about some of the weed life cycles. Now, the first one, and probably the one we deal with primarily in corn and soybeans, are the annuals. Now, these are species that complete their life cycle, and by that I mean from seed to seed. They germinate from the seed, and by the time that they reproduce seed, that time period is within 1 year, typically within one growing season. Now, annuals we can break down between winter annuals and summer annuals. The winter annuals germinate in the fall, they overwinter in a kind of a dormant state, and then they begin growing again in the spring and complete their life cycle early in the spring. We typically find, of course, the winter annual species in more of our no-till situations where we're not disturbing the soil any in the fall. Whereas summer annuals germinate in the spring, they can continue growing throughout the summer with the crop, and then complete their life cycle by the time that the fall of the season rolls around. So we've got the annuals. We can break down annuals, classify those as winter annuals versus summer annuals. Primarily, of course, early in the season, if we're dealing in a no-till situation, we have to control our winter annuals before we plant the crop. The rest of the season we'll be dealing primarily with summer annuals. Now, the biennials are plants that complete their life cycle within 2 years. Biennials will typically germinate during the warm season of the first year of their life cycle. After they germinate, they typically will overwinter in what's called a rosette stage. And a rosette stage is the plant does not grow upward very much from the soil. It tends to grow pretty close to the soil surface in a large arrangement, and there's large concentrations of leaves right near the soil surface. And that's what's referred to as a rosette stage. Now, during the second year, what they call is bolt. And by that we mean they have a period of very rapid growth where they send up their seed stock, set the seeds, and complete their life cycle. Now, some of the examples of biennials that we do deal with, a couple of the thistles, the bull thistles and the musk thistle. And another one, of course, up there is wild carrot. And finally, when we talk about perennials, we're talking about plants that can live more than 2 years. For example, one of the perennials that we're dealing more and more with in this state and also surrounding states in no-till is hemp dogbane. We're also seeing other perennial species, just for example, like common milkweed. These are plants that can grow year after year after year. They don't complete their life cycle in 1 to 2 years. They could be there theoretically indefinitely. Now, the perennial species can produce either seeds or they can reproduce by these vegetative propagales, and we talked about that a little bit earlier. Now, we can break down perennials like we did annuals into simple perennials versus spreading perennials. And the difference is that simple perennials do not have these vegetative propagales. For example, a dandelion growing out in a no-till field or in your yard sets that little white fluffy seed head, and that's how that dandelion reproduces. Whereas something like a hemp dogbane can also have a flowered or a seed head on it, but it is a spreading perennial because it also has an extensive underground root system that can increase the area of infestation of the plant without the use of seeds. Overall, probably spreading perennials, of course, are more difficult to control than simple perennials. Just think for a minute of trying to control dandelion versus trying to control the spreading perennials such as hemp dogbane. Now, how does control of these annuals versus perennials differ? As we said, primarily we deal with annuals during the growth or the growing season of the crop. However, we are, of course, seeing more and more perennial species becoming prevalent, especially in areas where we're not tilling the soil anymore. Now, annuals, primarily here we're going to be talking about the summer annuals. They're best controlled either mechanically or chemically at an early stage of growth. As the plants become more mature, they become, let's say, less susceptible or more difficult to control either mechanically or chemically. As the plant grows, of course, we notice more of the top growth or the above ground growth. But there's also a tremendous amount of growth going on with the root system. The larger the root system gets, even on annuals, the more difficult it's going to be for control, again, either chemically or mechanically. Now, if we deal with soil-applied herbicides, which we are here in this state, we use a tremendous amount still of soil-applied herbicides. To control annual weeds, they control these weeds after the seeds germinate. There are hardly any that I know of soil-applied herbicides that prevent seeds from germinating. Rather, the seed must germinate first. The radicle of the plant must come out, permeate through the seed coat, initiate growth before that herbicide is being able to be taken up into that seedling. Now, if we want to deal instead of soil-applied herbicides with post-emergence, again for annuals, it's better to control them at an earlier growth stage. If we read many of our post-emergent herbicide labels, we'll see that at a lower or a smaller growth stage for many species, we can use a lower rate. For example, if you look on the bassagran label, let's say, You may have 2 or 3 different rates according to what the weed size are. As the weed gets taller, as it gets larger, more mature, the susceptibility of that to the herbicide diminishes. It becomes more difficult for that plant to grow, or for that plant to be controlled. Now if we switch over and talk about a difference between an annual or a perennial, if we deal with trying to control it mechanically or chemically, we have to control both the above ground and below ground portion of that plant. Perennials are perennials for the simple fact that they can store a tremendous amount of reserves, food reserves in the root systems. That allows the top growth of the plant to die in the fall, winter of each year. But with those vast reserves of food in the root system, those food reserves are mobilized in the spring. That's what that plant uses to send up new shoots in the spring. So we have to have some type, either a deep type of a tillage to disturb that root system, or if we have to deal with it chemically, we have to select some type of a herbicide that will translocate and get down into those root systems. And overall, perennials, of course, are easiest to control before they, let's say, before they become perennials. And by that I mean early in the first year of their growth. As we go out and scout the fields, we need to be able also not only to identify annuals at an early stage, but we also need to start paying more attention to perennials. If you're dealing in an area where if you have one of your customers say you're starting no-till, probably after the first to second year, if you're out there scouting the field, not only pay attention for identifying annual weeds, but also identify the perennials. Because the first time that you see those perennials will probably be the easiest time to try to control them. If you've got a no-till field that's been no-tilled for many, many years, chances are when you go out that spring to look and scout for weeds, these perennials that you're seeing there are probably more established. So if we can control them before they develop that extensive root system, it's much easier and much more effective. If we do have an established stand of perennials and we do decide to try to control it chemically, as we said, we need to select a herbicide that will translocate down into those root systems. And when, of course, is the best time to apply that herbicide to get it down to the root systems? Well, for perennials, as we said earlier, they store those food reserves in the roots. In the spring, those reserves are mobilized back up to support new shoot growth. In the spring of the year, let's say we have everything moving upward. Well, if all the food reserves are moving up, it's going to be difficult for a herbicide to move down into the root system. Now, during the early fall of the year, the perennial is probably responding to a shorter day length. Temperatures are starting to drop. It's getting a little bit cooler in the night. The plant senses, hey, it's winter's coming. I better start storing up food reserves down in the root system so I can overwinter and then initiate new shoot growth the following spring. In the fall of the year, then, most of the movement of reserves of foods in the perennial species are downward. So overall, if we want to try to control perennials chemically, the best time to do it is late summer to early fall, when we can catch that translocation system moving down into the roots. Let's talk a little bit more now about herbicides. We'll get away a little bit from the weed biology and identification, talk more along the lines of herbicides. And we generally group herbicides, and we probably do this so we can keep job security and justify our employment in the world if you're at the university. But anyway, we group the things primarily to make it easier to discuss. If we can group a particular herbicides into one family, we can generally draw a lot of characteristics that are common to that whole entire family. We can classify things by how we apply them. Some materials, of course, we have to incorporate due to volatility problems if we leave them on the soil surface, due to photodegradation where the herbicide breaks down in the sunlight. We can also classify them according to pre-emerge. Or there are some, of course, that have no soil activity and only are effective post-emergence. So application method is one way for classifying herbicides. We can also talk about the chemical structure of the herbicide, and a little bit later we'll see some of these structures, and we'll go through these systems again. Now when I say I want to use a triazine herbicide, I could be talking about atrazine, I could talk about cyanazine, or I could be talking about metribuzin. When I say triazine herbicides or sulfonylurea herbicide or diphenyl ether, there I'm talking about what the chemical structure of that family is. And I'll show you some drawings of those in just a few minutes. But we also classify them by mode of action. By mode of action, we mean how does this particular family of herbicides work within the plant to kill that plant. As we've been talking about, especially when we're dealing with perennials, some of these herbicides are capable of moving within the plant. If they can move extensively in the plant, we call these things translocated herbicides. And as we say, translocated versus contact is probably not the best terminology in the world, but it's what we deal with right now. How do they translocate? Well, we can translocate particular herbicides in the xylem or the water conducting tissue, or they can translocate in the phloem or the food conducting tissue. Some herbicides, depending on how we apply them or when we apply them, may be able to move in both at the same time. We call those ambimobile herbicides. Translocation can depend, of course, on how we apply it. For example, let's talk about atrazine for a minute. If we apply atrazine to the soil and it's taken up by a growing plant, it's able to move in the xylem or the water conducting tissue of that plant. So in that case, it's mobile. If we wait and apply atrazine as a post-emergence application, it moves very little in the plant. So it's more or less reduced down to a contact. So translocation can also depend on how and when we apply that herbicide. Now, there are several principles governing herbicide action, and these principles pretty well hold true regardless of family, regardless of classification, or regardless of application. Now, the first one says to effectively inhibit plant growth, the herbicide must be able to reach its site of action within the plant. That's very simple to understand. We have to get it in there where it needs to be in order to kill the plant. To give you an example of this, say we're out in the field and we make a post-emergent herbicide application. And let's say 5 minutes after we pull out of the field, we're heading back to the plant. Here comes a thunderstorm and we get dumped on with an inch of rain. Now, we're probably not going to get very good control from that post-emergent herbicide, are we? Simply because that rainstorm came up so fast, it probably washed a lot of that herbicide off the leaf surface. It restricted that herbicide from reaching its site of action within that plant where it needed to be. Now, not only do we have to get it where it needs to be, we have to get enough of it there in order for it to effectively inhibit whatever process it works on. For example, this spring we had numerous calls and reports about poor performance of burn-down herbicides for no-till. You know, we had to sit back and scratch our heads for a minute. Now, why did we get such poor performance from, say, Roundup or 2,4-D, where for many years we've had a very good control with those particular materials? Well, at the time a lot of the burn-down herbicides were going on, we had a stretch in there of several nights where the temperatures got down into the upper 30s or low 40s. We probably got some of the material into the plant, of course, but with those low nighttime temperatures, the weeds probably were not growing very well or very actively. If they're not actively growing, they're probably not moving a lot of materials around or translocating a lot of materials in their systems. Well, one of the things that happens to be in there is the herbicide. So with those cool nighttime temperatures, we probably did not get enough of that herbicide where it needed to be to kill the plant. Once we get it to the site of action at a high enough concentration, it has to stick around long enough to inhibit that process. Now, this last point up there, we can probably discuss this in easier term by what's called metabolism. When a foreign compound enters a plant, whether it be a herbicide or whatever, that plant tries to break down that foreign compound. It doesn't like being invaded, let's say. When that herbicide gets into that plant, it tries to break it down also. Now, the majority of our selective herbicides for corn, for soybeans, or for wheat, the reason that they do not kill the crop but only kill the weeds is that the crop is generally able to break down these herbicides faster than the weeds can. Say if we apply a post-emergent herbicide to soybeans, if the herbicides are capable of breaking that material down in 1 to 2 days, the crop is probably not going to show much of an injury symptom. Say if we have weed species out there, let's just say red root pigweed, let's say. If that same material happens to stick around in that plant for about 25 to 30 days, that's just too long for it to be in there in order for that plant to survive. Okay? As we said, these principles can pretty well govern herbicide action regardless of family or regardless of application method. Many causes of weed control failure can be traced back to one of those principles not coming true or not being allowed to be completed. Let's talk about herbicide timings. Early pre-plants become pretty popular, used primarily, of course, in no-till. What we do with an early pre-plant, we go out anywhere from 14 up to 45 days ahead of planting, apply the herbicide, and this generally reduces our need for a burn down at planting time, or at least we hope it does. For our soil-applied grass materials and corn, the earlier we go out, the greater our likelihood that we may receive some type of precipitation in order to move that herbicide into the soil. Adequate moisture, of course, is required. If we do not incorporate these things, as we do not incorporate into no-till, if it's just laying on the soil surface, it's probably not going to give us very good weed control. We found that out this year, didn't we? Northern part of Illinois, a lot of the herbicides went out either early or pre-merge without incorporation, and we had very poor grass control in corn. We never got any moisture soon enough after the application to move that material down into the soil, into that seed germination zone where the weed seeds are germinating. Now, pre-plant incorporated, of course, we're applying the material to the soil and mechanically working it into the soil. This does eliminate our need or dependence somewhat on rainfall, but it does not totally eliminate the requirement of rainfall for herbicide activity. By mechanically incorporating it, we're placing more of that herbicide in that zone where the grasses or where the broadlead species are germinating. And again, some of our pre-plant incorporated materials are required to be incorporated. For example, eradicane or sutan have to be incorporated because these are volatile herbicides. If we don't incorporate them, they'll volatilize to the atmosphere and we'll end up with very poor weed control. The pre-emergence, these are the ones that we can put on if we prior to crop or weed emergence. As with the early pre-plant applications, these are dependent on rainfall for adequate control. If we apply these things after we plant a crop, it's even more dependent on rainfall because there we've pretty well eliminated any type of mechanical incorporation. And finally, then we'll talk about the post-emergence. Of course, post-emerge products are applied after the crops and weeds have emerged. They're made directly to the plant surfaces themselves. Applications post-emergence, of course, are timed according to this growth stage of the crop and of the weed. As we talked a little bit earlier, if we go out with an early post-timing, we can a lot of times use a lower rate of a particular herbicide. Now, of course, that we'll have to read the label on whatever material we choose to find out if we can do that. But generally, smaller weeds are easier and more susceptible to a particular herbicide and much easier to control. And many weed species we can control at a lower rate also. The post-applications, of course, minimize many of the interactions that we have with a soil-applied herbicide with the soil. There we're talking primarily about the adsorption, potential for leaching, etc. All the factors that can restrict that herbicide from being available for plant uptake. Well, the post-emergence applications tend to eliminate this. However, as we minimize some of our soil factors and interactions with the herbicide, when we move into post-applications, we find that we're more sensitive to differences and changes in the environment. Temperature and relative humidity play a very large influence on the efficacy of our post-emergence products. And probably with any post material, whatever it is, the most critical thing to get good weed control is to make sure we apply the thing when it should be. Application timing is critical. And most of our post materials do require some type of an additive in order to get optimal performance. There are some, of course, that don't need an additive, or that we can add an additive to because we increase the crop phytotoxicity or crop injury. Some of these additives may be selected for based on the prevailing environmental conditions. There are certain herbicide labels that have tables in there according to what the temperature is, what the relative humidity is. When you put those two together, then it tells you what type of an additive to use. So it's really not as simple as just pouring some surfactant or oil in there. It'll depend on what the herbicide is, to some degree what weed we're going after, and even what the prevailing conditions are when it's hot and dry. We generally have better performance from post-emergent herbicide if we use oils than we do surfactants. But not all of our post products allow the use of oils. So we have to always read the label to find out what we can use, what rate we need to use, and even what we shouldn't use. When we talk about additives, we generally break these down in different types of additive families. We talk about spray modifiers that just alter the physical characteristics of the spray solution. We can talk about utility adjuvants that broaden the spectrum which a particular herbicide can be applied under. Utility adjuvants such as compatibility agents, if we're mixing and applying, let's say if we want to apply a fertilizer with a chemical at the same time. There are some instances where we may need a compatibility agent to make sure we get everything mixed accordingly and mixed thoroughly. Activator adjuvants are probably the ones we use most often. Very simply, these enhance the performance of our post-emergence materials. Here we're talking primarily about our surfactants and our oils. These are the ones that we deal with more commonly. Fertilizers also, such as 28% UAN, very common, ammonium sulfate. One thing you need to keep in mind though, the spray additives do not enhance the performance of soil-applied herbicides. Now, by these we're talking primarily about the activator adjuvants. For soil-applied herbicides we may need something like a compatibility agent or an anti-foam agent, but any type of one of these activator adjuvants essentially do us no good with soil-applied herbicides. What are some of the functions of these additives? What specifically do they do in order to increase the efficacy of our post-emergence herbicides? Well, it may aid in retention of the herbicide on the leaf surface. Remember, we use the example of rainfall occurring about 5 minutes after post-application. We need to be able to retain that on the leaf surface. It may help in penetration of that herbicide into the leaf. It may help again in our mixing or reduce drift. Now, if we talk surfactants, they primarily increase the retention of the herbicide on the leaf surface. If you ever happen to take a drop of water from an eyedropper, put it on a leaf surface of a particular weed, it's probably going to run right off of there. That leaf surface is covered with a waxy layer. That waxy layer is called the cuticle, and the plant has that waxy layer to prevent excess water loss. Well, if water can't get out, it's kind of hard for it to get into through that waxy layer. And if you put another drop of water, have a little bit of surfactant in there, you'll see that drop spreading out over the leaf surface and not just remaining in that ball and running off the leaf. Our crop oils also aid in retention on the leaf surface, and they also help to keep that spray droplet moist. If the droplet dries too fast before the herbicide can penetrate through the leaf, we may actually get a crystallized herbicide deposit on the leaf surface. Now, if the material crystallizes or dries out too fast, it's going to be probably result in very poor weed control. Now, the oils, of course, also aid in the penetration of the material through the leaf surface. It may actually solubilize some of the oil in the cuticle and allow that herbicide to pass through there and get into where it needs to be. We classify the oils primarily on what they're based off of, either petroleum base or vegetable base. We got the petroleum oils or the vegetable oils. Now again, even within the oil classification of petroleum versus vegetable, some particular herbicide labels will allow the use of one or both. So we have to again read the label to find out what we can use. Some may specify only a petroleum base and no vegetable oils. One may say only vegetable but not petroleum. Ammonium fertilizers, we use those primarily with our post herbicides to target velvet leaf. use a 28%, we've got the ammonium sulfate. Those are probably the two that we use most often. Let's talk now about some principles of foliar-applied. We talked about some of the principles of herbicide action overall. Now let's break that down even a little bit further and talk about the principles of soil-applied and foliar-applied. So we talked first about foliar-applied. There's a sequence of events that has to happen in order to get good weed control of that foliar-applied herbicide. And first of all, the herbicide has to intercept the leaf surface. And once it's on that leaf surface, it has to be retained on that leaf surface. Again, if we put that drop of water on the leaf surface, it's probably going to roll right off of there. So we have to get it there, we have to retain it there, and it has to move through that leaf surface to get into the plant itself. Herbicide that just sits on the leaf surface is not going to control the plant. Once we get it into the plant, again, it has to be able to move where it needs to be within that plant. It has to move to its site of action. Once it gets to that site of action, it has to do something, doesn't it? And that do is what we call the mode of action of a herbicide. Now we can say a big long definition up there, the metabolic or physiological process impaired or inhibited by the herbicide. But a very easier way to remember what mode of action is, it essentially is how the thing kills the plant. These herbicides target specific processes within the plant, disrupt these processes, and that ends up with a lethal response to the weed. Now let's switch over to soil-applied herbicides. We're going out and applying them to the soil. Again, they must be absorbed into the plant for effective control. If they're only in the soil solution, the plant's not taking it up, we're not going to get weed control. It must be in the solution phase or in a vapor phase to be absorbed by the seedling. In a dry year, our soil-applied herbicides generally do not look that good because we don't have that much herbicide in solution in order for those seedlings to be able to take it in. And as we mentioned earlier, they don't prevent seed germination. The seeds go ahead and germinate as they're trying to establish the root system, emerge from the soil. That's when they're absorbing this particular herbicide, whatever it may be. And many times with some soil-applied herbicides, a lot of times you won't even see any weed seeds or weed seedlings emerge from the soil. So a lot of people think that it's preventing the seeds from germinating. Actually, the weed seedlings probably died before they reached the soil surface. The site of absorption, where a particular herbicide is absorbed into the plant, can vary by herbicide and by grass or broadleaf type of weed species. Grasses will generally absorb more herbicide in the shoot region, whereas broadleaf will primarily absorb the herbicide by the root system. So this can have a little bit of an influence on where we want to place this herbicide. For example, our grasses. Most of our annual grasses and our corn and soybeans will germinate in the top half-inch of soil. So if we have a soil-applied herbicide and want to incorporate it, we probably don't want to incorporate it down to 2 inches, 2 or more inches, because most of our seeds, grass seeds, are germinating above it. And again, they absorb it primarily in the shoot zone. So shallow placement for grass control. For broadleaves, if they absorb primarily by the root system, we'll need a little bit deeper placement. Now, unfortunately for broadleaves too, we have differences in the depth of germination depending on if it's large-seeded or small-seeded broadleaf. Small-seeded broadleaf, of course, germinates fairly shallow like the grasses do. Larger-seeded broadleaf will generally germinate from a deeper depth. Well, let's talk just a little bit more about mode of action, and we'll open her up for questions. We ask ourselves, why do we want to study herbicide mode of action? Well, I kind of know why you guys want to study herbicide mode of action. You got a test coming up. But there's several other reasons why to study it. First of all, if we know how a herbicide works within a plant, how does it kill that plant? We said earlier when we were talking about families that most of the families have some type of characteristics to them. Well, if we know the mode of action, a lot of herbicides in the same family give us characteristic injury symptoms. If we know how the thing works in the plant, if we say it's a photosynthetic inhibitor, we're probably going to be looking for injury symptoms like leaf burning, bronzing, or speckling. And we wouldn't expect that from something, let's say, like an amino acid inhibitor. We wouldn't see the same type of an injury symptom. If we know how a material works in the plant, we may be better able to diagnose the injury in the field itself. Now, a lot of times when we work out the plant clinic during the summer, we get a lot of samples out there for diagnosis of injury. Unfortunately, a lot of those samples may have been in the mail for several days. And some of the symptoms that we look for may not be as prevalent after the thing has been sitting at the post office for a while before we get to it. So it'll help us better ID the symptoms in the field if we know how a herbicide works. Probably even a factor also that's very important, is becoming more important, is we need to understand how these things work in the plant, how they kill the plant, so we can avoid the development of resistant weeds. Now, this could be a bigger problem coming up in the next few years. Now, resistant weeds, what's that mean? Well, it means primarily that our return on our herbicide investment is going to be reduced. If you're a commercial dealer or applicator, if you apply a particular herbicide to a field that has resistant biotypes in it, your customers are probably not going to be very happy because they're not going to get very good weed control. Now, by mode of action, we defined this earlier, but I put this one in here because there's a difference between mode of action and site of action. The mode of action, of course, we said, is how the thing kills the plant, a particular process inhibited by the herbicide. A photosynthetic inhibitor interacts with the process of photosynthesis. A pigment inhibitor interrupts the biosynthesis of some of the pigments of the plant. Now, mode of action is different from site of action. When we talked about site of action, we were talking about principles governing effectiveness. Site of action is the actual physical location in that plant where that herbicide binds to. Okay. Give you an example. Say if we talk about atrazine. The mode of action of atrazine is a photosynthetic inhibitor. The site of action of atrazine is on the D2 protein in the electron transport chain. Now, a lot of times you hear these terms being used kind of interchangeably and kind of loosely. But we need to try to keep the thing straight and understand that there is a difference between mode and site. We've already talked about this a little bit, how we classify them. I just wanted to give you some examples. Pre-emerge, Preplant incorporated, something like Command generally is incorporated unless you go with their early label. Eradicane requires incorporation due to volatility. Some of our post-emergence products have very little soil activity, so they have to be applied directly to the plant. Chemical structure. Here's what we say when we talk about a sulfonylurea. It has this basic backbone to chemical structure, or phenoxy, or dinitroaniline. This is what we're referring to. We get different herbicides within these classifications or within these families based on different substitutions on these rings and different patterns. But these are the terms here that we'll see most often when we talk mode of action. As we said, it's something like a photosynthetic inhibitor, pigment inhibitor, an ACCase inhibitor. Now, I see we don't have time to go in through various families of these particular inhibitors. Now, where do you find out what falls into what category, and what the mode of action of these, and where these things work, and what a little more information on the mode of action? Well, in the scouting manual in Chapter 5, there's a piece in there in the new revised edition of the scouting manual that discusses herbicide mode of action. I wrote the thing and I've tried to simplify it as best I can to try to take all the scientific information and try to condense it down in a more easy to understand format. For each of the various families, I've tried to go through there and give some background on the plant systems. For example, if you've forgotten what photosynthesis is, and I'm standing up here talking about a photosynthetic inhibitor. Well, in this chapter, before I talk about photosynthetic inhibitor, they give you some background on the process of photosynthesis. I do that for the simple fact I hope that by understanding the process, you may be able to comprehend a little bit better what happens when we block this process. Within each family in there, I also try to break down the more commonly used herbicides into families, so you know which particular herbicide falls into which particular family. Now with that, I see we've got about 5 or 6 minutes left, so we'll open it up for questions. It's almost a silly thing to ask for questions 5 minutes before lunch, isn't it? Yes, sir.
Specifically now, there's some of the manufacturers that are talking about adding a different mode of action to the tank mix, number 2, 3. You feel we're delaying resistance, or are we stopping the resistance?
Okay.
I think that area.
The question was on in particular the ALS herbicides, adding in tank mixing a second herbicide that has a different mode of action. That can delay the onset of resistance if we do it right. By that I mean if we are concerned about a particular species developing resistance. Say I'm concerned about a pigweed being resistant to an ALS material. What I want to tank mix with my ALS material is a herbicide that is also very effective on pigweed that has a different mode of action. For example, say if we want to use Pursuit in our soybeans, and we're concerned, we've used it for several years, we're starting to think about it. If our primary concern is with pigweed, I have to pick a tank mix partner. If I pick Basagran as a tank mix partner, I'm probably not doing myself much good, am I? For the simple fact is, Basagran is not very effective on pigweed. So I'll have to pick something like a diphenyl ether that has pretty good pigweed activity, tank mix in with my ALS material. To use a tank mix strategy, both tank mix partners have to have substantial activity on the weed species that you're concerned about in order to make something like that work. Will tank mixes slow the onset of resistance? They'll definitely help us. It may slow it, it may not prevent it. It's difficult to tell.